For millennia, humanity has gazed upon the night sky, a boundless tapestry of stars and galaxies, and pondered one of the most profound questions. Does space ever end? This isn't a simple question of reaching an edge, but a complex inquiry into the very fabric of existence, stretching the limits of our understanding and challenging our perceptions of infinity. The concept of end in space could refer to a physical boundary, a dimensional limit, or perhaps a frontier beyond which our known laws of physics cease to apply. From the earliest civilizations, observations of the celestial sphere shaped our understanding. Ancient Egyptians envisioned a goddess, Nut, arched over the earth, her body forming the sky. The Babylonians charted constellations, seeing order in the heavens, but still within a finite, flat earth cosmology, with space as a dome above. Their universe, though vast to them, had clear limits. The ancient Greeks, however, began to introduce more abstract thought. Philosophers like Anaximander proposed an apeiron, an infinite, boundless, and undefined primary substance from which all things originate. While not explicitly about the physical end of space, it was an early conceptualization of the potentially limitless nature of the cosmos, moving beyond simple enclosed models. Aristotle, a dominant figure in ancient Greek thought, argued for a finite, hierarchical, geocentric universe. He believed the Earth was at the center, surrounded by crystalline spheres carrying the planets, moon, and stars, all enclosed by a final, outermost sphere of fixed stars. Beyond this sphere, he argued, there could be no space, no void, as it would be superfluous and contradict the natural order. Ptolemy, a Roman astronomer in the 2nd century AD, further formalized this geocentric model in his work, The Almagest, which became the standard astronomical text for over 1400 years. His complex system of epicycles and deferents successfully predicted planetary motions, reinforcing the idea of a finite, Earth-centered cosmos, bounded by the sphere of fixed stars. During the scholastic era of the Middle Ages, Christian theology largely integrated Aristotle's finite, geocentric universe. While God's power was infinite, the created cosmos was often perceived as finite and perfect, reflecting a rational, divinely ordered design. The question of what lay beyond the ultimate sphere often invoked discussions about the realm of God and angels, rather than physical space. The Renaissance brought a new spirit of inquiry and observation. Thinkers like Nicholas of Cusa dared to suggest an infinite universe long before scientific evidence emerged. He posited that since God is infinite, his creation, the universe, must also be boundless and without a center, a radical departure from the prevailing Aristotelian view. Giordano Bruno, an Italian philosopher burned at the stake in 1600, was another bold proponent of an infinite universe, filled with countless stars, each potentially a sun with its own planets, perhaps even inhabited. His vision, though not scientifically proven at the time, was profoundly insightful for its break with the finite, human-centric cosmos. Nicolaus Copernicus, in the 16th century, shifted the Earth from the center of the universe to being just another planet orbiting the Sun. His heliocentric model, while revolutionary, still maintained a largely finite, stellar sphere at its outer edge, containing the fixed stars. It expanded our perspective, but didn't immediately shatter the idea of an ultimate boundary. Galileo Galilei's telescopic observations in the early 17th century provided crucial empirical support for the Copernican system. He discovered moons orbiting Jupiter, phases of Venus, and that the Milky Way was composed of countless individual stars. These discoveries hinted at a far vaster, more complex universe than previously imagined, beginning to erode the idea of a simple, finite stellar sphere. Isaac Newton's Laws of Universal Gravitation, published in 1687, provided a comprehensive framework that elegantly explained the motion of planets and objects on Earth. His laws implied a universe where forces operated across infinite distances, leading many natural philosophers to conceive of an infinitely large, static universe, populated with stars spread throughout. However, an infinite static universe posed a paradox. If gravity acts everywhere, an infinite distribution of matter should collapse in on itself or lead to infinite gravitational forces. This was one of the early theoretical challenges to the idea of an endlessly filled, unmoving cosmos, foreshadowing future discoveries about its dynamic nature. While Newton's laws suggested an infinite arena, further understanding required stepping beyond our solar system. The 18th century saw debates about the nature of nebulae, fuzzy patches of light in the night sky. Were they merely clouds of gas and dust within our own galaxy, or were some of them distant island universes akin to our own Milky Way? William Herschel, a pioneering astronomer of the late 18th and early 19th centuries, meticulously mapped the stars of the Milky Way, attempting to determine its shape and size. He concluded that the solar system was embedded within a large, disc-shaped collection of stars, but his observations didn't definitively resolve the ninso, Slakey, ninso, mamatine term enso, Psykerm enso, nenso, Psyker mamatine term. The development of spectroscopy in the 19th century allowed astronomers to analyze the light from celestial objects, revealing their chemical composition and motion. This new tool would prove invaluable in understanding the true nature and immense distances of these mysterious nebulae, moving beyond mere visual observation. The Great Debate of 1920 between astronomers Harlow Shapley and Heber Curtis epitomized the uncertainty surrounding the scale of the universe. Shapley argued that spiral nebulae were relatively small and part of our Milky Way galaxy, while Curtis contended they were independent galaxies, vast distances away. The true scope of space hung in the balance. The key to resolving this debate came with Edwin Hubble's observations in the 1920s, using the powerful 100-inch Hooker telescope at Mount Wilson. He was able to identify individual stars, specifically Cepheid variables, in the Andromeda Nebula, a type of star with a known relationship between its pulsation period and intrinsic luminosity. By measuring the apparent brightness of these Cepheids in Andromeda, Hubble could calculate their immense distance, definitively proving that Andromeda was not a nebula within our galaxy, but an entirely separate galaxy, millions of light years away. This discovery single-handedly expanded the perceived size of the universe by orders of magnitude. Hubble's groundbreaking finding meant that our Milky Way was just one of countless galaxies, each itself a colossal collection of billions of stars. This immediately shattered the earlier, more confined models of the cosmos and established the universe as a truly immense, multi-island structure, shifting our understanding of space's scale forever. Furthermore, by observing the light from these distant galaxies, Hubble and his colleague Milton Humason noticed a peculiar phenomenon. The light from nearly all galaxies was shifted towards the red end of the spectrum, a phenomenon known as redshift. This was similar to the Doppler effect for sound, where the pitch of a siren changes as it moves away. This systematic redshift of light from distant galaxies meant they were moving away from us, and the farther away they were, the faster they were receding. This was not just a few galaxies moving, but a universal outward motion, leading to the inescapable conclusion that the universe itself was expanding. The expansion of space is perhaps the most profound discovery in cosmology. It means that the space between galaxies is literally stretching, not that galaxies are simply flying through pre-existing space. This stretching fundamentally alters our intuitive understanding of ends or boundaries in space. If the universe is expanding, then logically, if we rewind time, it must have been smaller in the past. Tracing this expansion backward, cosmologists arrived at a moment when all the matter and energy in the observable universe were compressed into an incredibly hot, dense state. This singularity is the foundational concept of the Big Bang Theory. The Big Bang Theory describes not an explosion in space, but an expansion of space itself. It suggests that space and time began together approximately 13.8 billion years ago. Before this moment, conventional physics breaks down, meaning the question of what was before the Big Bang or outside it may be meaningless within our current understanding. A critical piece of evidence supporting the Big Bang came in 1964 with the accidental discovery of the cosmic microwave background radiation, or CMB. Arno Penzias and Robert Wilson, while testing a new antenna for Bell Labs, detected a persistent, uniform hiss of microwave radiation coming from all directions in the sky. This faint glow was quickly identified as the afterglow of the Big Bang, the residual heat from an early universe that cooled enough for photons to travel freely. The CMB is almost perfectly uniform, suggesting the early universe was remarkably smooth and isotropic, meaning it looked the same in all directions. The uniformity of the CMB is a powerful indicator that the universe, on large scales, appears quite homogeneous. Matter and energy are smoothly distributed. This cosmic principle, known as the cosmological principle, suggests that no matter where you are in the universe, on average, it looks the same. This implies no discernible center or edge to space. Despite the universe's overall uniformity, there are tiny fluctuations in the CMB temperature. These minute variations, on the order of 1 part in 100,000, are crucial. They represent the primordial seeds of structure, the slight density differences that over billions of years grew into the galaxies, clusters, and superclusters we observe today. The Big Bang model, supported by the expanding universe and the CMB, implies a universe with a definite beginning in time. But what about its extent in space? Does the expansion mean it has an edge that is constantly moving away from us, or is it genuinely boundless? This leads us to the concept of the observable universe. The observable universe is the part of the universe that we can theoretically see from Earth. Because light travels at a finite speed, there's a limit to how far light has had time to travel to reach us since the Big Bang. This limit defines our cosmic horizon. Even though the universe is only 13.8 billion years old, the observable universe extends much further than 13.8 billion light-years in radius. This is because space itself has been expanding during the time the light has been traveling. So a galaxy whose light took 13 billion years to reach us is now approximately 46.5 billion light-years away. The observable universe is a sphere centered on us, the observer. An observer in a distant galaxy would have their own observable universe, which would partly overlap with ours but also extend into regions we cannot see. This means our cosmic horizon is personal, not a universal boundary of space itself. So the observable universe is finite, but this doesn't mean the entire universe is finite. It simply means we are limited by the speed of light and the age of the universe. The true extent of the universe beyond our cosmic horizon remains unknown and unobservable to us. One of the most intriguing aspects of the universe's expansion is its acceleration. For a long time, scientists expected the universe's expansion to slow down due to gravity pulling matter together. However, observations from the late 1990s revealed the opposite. In 1998, two independent teams of astronomers studying distant supernovae unexpectedly discovered that the universe's expansion is not only continuing, but is actually speeding up. This accelerating expansion implies the existence of a mysterious force counteracting gravity. This mysterious force or energy causing the acceleration has been dubbed dark energy. It's thought to make up about 68% of the total energy density of the universe, yet its nature remains one of the greatest puzzles in modern cosmology. It is an intrinsic property of space itself. If dark energy is a constant property of space, then as space expands, more dark energy is created, which in turn causes more expansion. This positive feedback loop could lead to an ever-accelerating expansion, with profound implications for the ultimate fate and perceived end of space. In a runaway expansion scenario, often called the Big Rip, dark energy could eventually become so dominant that it overcomes gravity, then the strong and weak nuclear forces, tearing apart galaxies, stars, planets, and eventually even atoms themselves. This would be a dramatic and total end to the structure of space. However, present observations suggest dark energy is more likely a cosmological constant, meaning the universe expands towards a state of infinite cold emptiness. Galaxies will eventually become so distant that they recede beyond each other's cosmic horizons, leaving isolated island universes in an ever-darkening void. This Big Freeze or heat death scenario is a more widely accepted ultimate fate, where space never ends but becomes increasingly dilute and cold, incapable of supporting complex structures or processes. The question then becomes not if space ends, but if anything within it will ever again interact across vast distances. Beyond its expansion and ultimate fate, another crucial question about space is its shape, or curvature. Just as a two-dimensional surface can be flat, positively curved like a sphere, or negatively curved like a saddle, the three-dimensional fabric of space can also possess intrinsic curvature. The curvature of space depends on the total density of matter and energy within it. If the density is exactly critical, space is flat, Euclidean geometry holds, parallel lines never meet, and the universe would likely be infinite in extent. If the density is greater than critical, space is closed, positively curved like the surface of a giant sphere. In such a universe, parallel lines would eventually converge, and though it has no edge, it would be finite in volume. If you traveled far enough in a straight line, you would eventually return to your starting point. In a closed universe, the expansion would eventually halt and reverse, leading to a big crunch, a catastrophic collapse back into a hot, dense state, effectively an end to space as we know it, converging back to a singularity. Conversely, if the density is less than critical, space is open, negatively curved, like a saddle. In this scenario, parallel lines would diverge, and the universe would be infinite in extent and would continue expanding forever at an accelerating rate. Current cosmological observations, particularly detailed measurements of the cosmic microwave background by probes like WMAP and Planck, strongly indicate that the universe is remarkably flat. This implies that the total energy density of the universe is very close to the critical density. A flat universe, if truly infinite, means that space never truly ends. It simply continues without boundary or limit. This challenges our everyday intuition, as we are accustomed to observing finite objects with clear edges. While observations suggest an overall flatness, the precision of these measurements isn't absolute. There's still a small margin of error, meaning the universe could be very slightly curved, either closed but extremely large, or open but with a very subtle negative curvature. The truly infinite nature remains inferred rather than definitively proven. If the universe is indeed spatially infinite, then any concept of an end to space becomes meaningless in a physical sense. There would be no edge to fall off, no barrier to hit, just more and more space, potentially filled with an infinite number of galaxies and structures similar to our own. However, even an infinite universe doesn't rule out the possibility of regions with different physical laws or properties. Our observable universe might be just a bubble within a much larger, potentially infinite and more diverse cosmos, a concept that leads us into the fascinating realm of the multiverse. The idea of a multiverse proposes that our universe, with its specific laws and constants that allow for life, is just one of many, perhaps infinitely many, universes. This concept arises from several theoretical physics frameworks, particularly string theory and eternal inflation. One version, the Level 1 multiverse or infinite expanse, suggests that if space is truly infinite and flat, then beyond our cosmic horizon, there must exist other regions of space with the same laws of physics and eventually, even exact copies of ourselves, just impossibly far away. The Level 2 multiverse arises from theories of eternal inflation. This proposes that while the Big Bang initiated our universe, inflation, a period of extremely rapid expansion, might not have ended everywhere simultaneously. Instead, regions might stop inflating, forming, quote, bubble universes within a larger, still inflating cosmic foam. Each such bubble universe in the Level 2 multiverse could have different fundamental physical constants, different numbers of dimensions, or even different sets of laws altogether. In this scenario, our universe is just one of countless distinct cosmic experiments. The Level 3 multiverse stems from the many worlds interpretation of quantum mechanics, where every quantum possibility branches into a new universe. Every decision, every random subatomic event creates a divergent reality. This implies an infinite number of parallel universes existing in the same space and time, but inaccessible to each other. Finally, the Level 4 multiverse encompasses all possible mathematical structures. This most abstract concept proposes that if something is mathematically possible, it exists as a universe. This is a highly speculative but profoundly encompassing view, where not only space but the very concept of reality is infinitely manifold. If a multiverse exists, the question, does space ever end, shifts. It might end within our specific universe, or it might be infinite. But even if our universe is finite, the space or arena in which the multiverse exists could be infinitely larger, rendering our universe a mere speck in a grander, unbounded reality. These multiverse theories, while compelling, are often highly theoretical and currently lack direct observational evidence. They push the boundaries of what can be scientifically tested, but they offer fascinating solutions to cosmic puzzles like the fine-tuning of our universe for life. The existence of extra dimensions beyond our familiar three spatial dimensions and one time dimension is another concept that challenges our understanding of space's extent. String theory, for instance, postulates that there could be up to 6 or 7 extra dimensions, curled up so tightly that they are imperceptible to us. Or, these extra dimensions could be large, but we are effectively trapped on a brane, a higher dimensional membrane within them. In this brane world scenario, Known space is just a slice of a much larger reality, and objects or even other universes might exist in these bulk dimensions beyond our reach. These additional dimensions, if they exist, would fundamentally alter our understanding of what space is and whether it can end. An edge in our three dimensions might lead seamlessly into another dimension, making the concept of an end relative to our current perception. The quest to understand space's ultimate nature is deeply intertwined with the search for a unified theory of everything, a theory that marries quantum mechanics, which governs the very small, with general relativity, which describes gravity and the very large. Quantum gravity theories, such as string theory and loop quantum gravity, offer potential insights into the very earliest moments of the universe and the structure of spacetime at its most fundamental level. These theories might eventually tell us if space is fundamentally continuous or discrete, like tiny pixels. If space is discrete, composed of fundamental quanta of space, a smallest possible unit, it would imply a granular structure rather than a smooth, infinitely divisible continuum. This granular nature might provide a new interpretation of what an end signifies. The ultimate fate of the universe is also central to the question of whether space ends. While the Big Freeze is the leading candidate, other theories remain. Could space, instead of infinitely expanding, eventually cycle through big bangs and big crunches in an oscillating universe? The cyclic universe model, while elegant, faces significant challenges from current observational evidence, especially regarding the accelerating expansion and the existence of dark energy, which seems to drive an ever-increasing separation, not a recollapse. Ultimately, the question, does space ever end, shifts from a purely physical boundary to a much deeper philosophical and existential inquiry. It forces us to confront the limits of human comprehension and our place within a potentially infinite cosmos. The very act of asking such a question defines our intellectual curiosity. It drives scientific inquiry, pushing the boundaries of our telescopes, our particle accelerators, and our theoretical models, constantly seeking to refine our understanding of reality. The unknown aspects of space's full extent remind us that our current scientific models, though powerful, are incomplete. Theories like string theory or loop quantum gravity are attempts to fill these gaps, proposing new ways to think about the fabric of reality, the fine-tuning of the universe. The observation that physical constants seem precisely calibrated for the emergence of life sometimes leads to arguments for a multiverse, where our universe is one of the lucky ones, or to philosophical debates about design. The concept of a mathematical universe, where reality itself is a mathematical structure, would imply that space in a sense never ends because mathematical structures are abstract and infinite. This takes the question beyond physical observation into pure abstraction. The vastness of space, whether finite but unbounded or truly infinite, profoundly impacts our perspective on our home planet. Earth becomes a tiny, fragile speck, emphasizing the urgency of caring for our unique blue marble in this immense cosmic backdrop. The exploration of distant exoplanets and the potential for life beyond Earth further expands our concept of space. Each new discovery of a planetary system or a potentially habitable world adds another pinprick of light to the seemingly endless cosmic canvas. The speed of light acts as a fundamental speed limit within our universe. This means that even if space is infinite, information from distant regions can only reach us if it has had sufficient time to travel, permanently limiting our observable horizon. The ultimate end to space might not be a physical boundary, but rather a cosmological horizon of possibility, a limit to what can ever causally influence us, due to the accelerating expansion pushing regions beyond our reach faster than light can travel. Einstein's theory of general relativity revolutionized our understanding of space, showing it's not a static backdrop, but a dynamic fabric that can be warped and stretched by mass and energy. This dynamism is key to its expansion and its potential lack of an end. Cosmologists continue to gather data from distant galaxies, the cosmic microwave background, and gravitational waves to refine their models. Each new piece of evidence helps us piece together the grand narrative of the universe's origin, evolution, and ultimate destiny. Telescopes like the James Webb Space Telescope push the boundaries of observation, peering back to the earliest galaxies forming just a few 100 million years after the Big Bang. These observations help confirm and refine our understanding of the universe's first moments. The question of whether space ever ends also ties into our understanding of time. If space is unbounded, does time also flow infinitely, or does it have a beginning and an end? The two dimensions are intrinsically linked in spacetime. Some theories propose a cyclical nature to time, or that time itself could be an emergent property of the universe rather than a fundamental continuum. If time could end, then perhaps the changing nature of space, including any end to its expansion or form, would also cease. The human mind, naturally finite, struggles with the concept of true infinity. We can extrapolate, but to truly comprehend an endless expanse, a dimension without a boundary, is a profound cognitive challenge. Yet, science continues to push these boundaries of thought. As we advance our understanding, the ends we perceive are often merely new beginnings or transitions to a deeper, more complex layer of reality. What once seemed like a limit becomes a gateway to further discovery. The cosmic web, the intricate network of galaxies, galaxy clusters, and vast empty voids, is the largest structure we observe. This web spans billions of light years, but even it is contained within the larger structure of the universe as a whole. The largest structures, according to the cosmological principle, begin to average out, ensuring that on sufficiently vast scales, the universe appears homogeneous and isotropic. This uniformity is a key indicator against a detectable physical edge. The early universe underwent a period of rapid inflation, smoothing out initial irregularities and stretching space to immense proportions. This inflationary epoch is crucial to explaining why the universe appears so flat and homogeneous today. Without inflation, the universe should be incredibly curved and heterogeneous, contradicting observations of the CMB. Inflation provides a mechanism for space to rapidly become flat and uniform, extending far beyond the observable horizon. The existence of dark matter, an invisible substance making up about 27% of the universe, also plays a role in shaping cosmic structure and influencing expansion. While not directly observed, its gravitational effects are evident. The precise densities of dark matter, dark energy, and ordinary matter collectively determine the universe's curvature and its ultimate fate, impacting whether its expansion ever ends or results in an everlasting cold void. The concept of a false vacuum decay is a speculative but intriguing possibility for how our universe, and thus space as we know it, could abruptly end. It suggests our universe might be in a temporary, unstable state. If our vacuum state, the fundamental energy level of space, were to transition to a lower, more stable true vacuum, a bubble of this new reality could nucleate and expand at nearly the speed of light, fundamentally altering or destroying the very fabric of space and reality within it. This end would not be a gradual cooling or a violent rip, but an instantaneous, fundamental alteration of physical laws, making the very concept of space unrecognizable or non-existent in its current form. However, this remains purely theoretical. The study of general relativity suggests that space and time are not separate but interwoven as space-time. If space were to end, it would likely mean the end of time as we know it, or a transition to an entirely different temporal dimension. The anthropic principle, a philosophical consideration, suggests that the universe's seemingly fine-tuned properties are not surprising, because if they were different, we wouldn't be here to observe them. This doesn't prove an infinite universe but makes perfect sense in a multiverse. The ongoing search for gravitational waves, ripples in space-time caused by cataclysmic cosmic events, offers another window into the universe's most extreme phenomena. These waves could carry information from regions otherwise hidden from us. Perhaps the end of space is not a physical boundary, but rather a limit to predictability or to our current physical laws. Beyond a certain scale or energy density, the known rules of physics might simply cease to apply, opening up new, unknown physics. The concept of information in the universe also raises questions about space's extent. If space is truly infinite, does it contain infinite information? And if so, what are the implications for computation, consciousness, and the very nature of reality? Some theories propose that the universe might be a hologram, with all the information contained on a distant two-dimensional surface. If true, this radically changes our perception of space's three-dimensional nature and what end could mean. The existence of mathematical constants, like pi, that are irrational and seemingly infinite in their decimal expansion, could be seen as an analogy for the universe's boundless nature, a fundamental property that simply continues without repetition. The cosmological principle's assumption of homogeneity and isotropy is a cornerstone of our Big Bang model. If this principle were to break down on even larger scales beyond our current observation, then the picture of a boundless universe might change. However, present evidence strongly supports the cosmological principle, implying that we do not occupy a special or central place, and the universe truly extends without end or unique feature, consistent with a flat geometry. The ongoing search for primordial gravitational waves, relics from the earliest moments of inflation, could provide definitive proof for the inflationary epoch. This would further strengthen the case for a universe that rapidly stretched to become immensely larger than our observable portion. The exploration of quantum foam at the Planck scale, the smallest possible unit of space and time, suggests a chaotic, bubbling structure. What defines space at this level, and how does it transition to the vast, smooth cosmos we observe? Could the universe be a finite but expanding bubble within a larger, non-expanding eternal void? In such a scenario, our space would indeed end at its boundary, but that boundary would exist within another, perhaps infinite space. The nature of nothing is also challenged by this question. If space ends, what is beyond it? Can there truly be nothingness, or is there always something, even if it's a different kind of existence or a pre-cosmic state? Our very existence, the flourishing of life within this vast expanse, compels us to seek answers. It's an innate human drive to map our reality, to understand our address in the cosmos, even if that address extends infinitely. The scientific method, through observation, hypothesis, and experimentation, is our primary tool in this grand cosmic quest. Every measurement, every new theory, refines our understanding inch by painstaking inch towards the truth. While we may never definitively observe all of space, the mathematical consistency of our current models, particularly the flat expanding universe, strongly suggests that what we see is a small part of a much larger unbounded reality. The question, does space ever end, remains one of the ultimate cosmic riddles, tantalizingly just beyond our grasp. But in seeking the answer, we unravel the deepest secrets of existence itself. The journey of discovery continues, propelled by new technologies, ingenious theories, and the relentless curiosity of the human spirit. Perhaps one day we will have a more complete answer, or merely a grander, more nuanced question. Until then, we stand on a tiny planet, orbiting an ordinary star, within one of billions of galaxies, in a universe that is either incomprehensibly vast or truly infinite. And in that uncertainty lies a profound beauty and inspiration. Consider the implications of true infinitude. If space is infinite, then all possible arrangements of matter and energy must eventually occur somewhere. This implies infinite variations of our own history playing out across the boundless expanse. This recurrence paradox within an infinite, eternal universe suggests that every event, no matter how improbable, is destined to repeat an infinite number of times. It's a mind-bending thought that challenges our unique individuality. However, cosmic expansion works against this recurrence for all but the very smallest scales. Even if space is infinite, the accelerating expansion ensures that most regions will eventually be causally disconnected, preventing information from infinitely repeating across accessible space. The concept of the holographic principle, hinting that all 3D information about space can be encoded on its 2D boundary, provides a framework that might reconcile finite information with vast, perhaps infinite, space. Could space itself be an emergent phenomenon, arising from a deeper, more fundamental reality that is neither spatial nor temporal in our conventional understanding? This would mean space, as we know it, potentially has a beginning and an end, in a way we can barely conceive. The possibility of space-time exhibiting foam-like properties at extremely short distances implies that the smooth fabric of space on our scales might break down into a chaotic, fluctuating realm. This challenges the very notion of a continuous end. The human capacity for imagination allows us to ponder these vast cosmological questions, to conceive of infinities and boundaries, even when our direct experience cannot verify them. It's a testament to the power of our minds. Regardless of whether space truly ends, its vastness and dynamic evolution force us to continually reevaluate our position and significance. Science provides the humility and the awe, while philosophy grants the contemplation. The journey of understanding the universe is never-ending, much like space itself might be. Each answer illuminates new questions, propelling humanity forward in its eternal quest to comprehend the cosmos. So, does space ever end? Current scientific evidence points to an expanding, very nearly flat universe that is likely infinite. While our observable universe is finite, the universe beyond our reach probably stretches without bound, an endless cosmic tapestry waiting to be understood, forever challenging the limits of our imagination.